Very good. Now, the next natural topic, once we have a sense of what magnetic field lines look like and how they behave in the case of at least one case, the case of a wire, the next thing we might want to consider is more complex situations. And the way we learned to handle field lines in more complex situations was by building a fluid analogy for the electric field case. So it's natural now to ask, is there a fluid analogy in the magnetic field case? So in order to determine what that analogy might be, it helps to consider this one case for which we do know the answer and ask ourselves whether a fluid can even behave in this way. So let's look for this fluid analogy. Well, the one case we know again is this infinite wire carrying a current here off to the left. And what we've just learned is that the magnetic field lines circulate around in circles. So let me try to sketch them. They come out in front, they go down behind and back, right? So I've got a whole series. So if this were a fluid situation, I need to find some way to get, this is the side view, or I can do the head-on view again. But now I can draw it a little more carefully, right? I'll have my current I coming out, and of course the fluid then is just, in this analogy, would be just traveling around in nice circles directly centered on my wire. Can I get fluid to circulate around like that, around an axis? What kind of mechanical model would do that? Well, certainly there are a large number of famous examples in fluid mechanics where you get just such a circulating behavior. If you think about it, this is exactly the type of pattern, if I were to stand it on its end, of what we expect and what we would see, for instance, in a tornado. Right? In a tornado, what you see is well, it's a little hard to draw the funnel cloud, but what you see then is the air is circulating around a central axis which is standing vertically against the ground. Now, this type of a thing has an actual name in fluid mechanics. This type of fluid flow pattern is called a vortex. And we can actually induce a vortex in the same fluid model that we've been discussing previously, right? An inviscid, incompressible Newtonian fluid flow model. In those cases, then, you can generate precisely this type of a flow pattern if what you do is take your wire, right? And I'm going to draw it as a finite wire here, just to give it a little bit of thickness, because it's a real wire that I'm going to put into a real fluid. And I'll take my wire to have a radius r that defines the thickness of this wire. And it turns out that if I set this wire into my tank of fluid, so here I'm going to draw my fluid tank, like so. I set him into that tank of fluid, and I set the wire rotating around with a special angular frequency, omega. Remember the rotation frequency. And in this case, the magic formula to make everything work out is to set it that equal numerically to mu naught times your current divided by 2 pi capital R squared, where capital R is the radius of your wire. And if you do that, you can prove within fluid mechanics that you will generate a flow field, a velocity flow field that circulates directly around your wire. Basically, just the surface of your wire starts to drag the fluid near it around in circles, and that fluid near it starts to drag neighboring particles of fluid that are further out around with it until you settle down to this steady state type of a flow pattern. And if you choose for your wire to rotate it at an angular frequency that is numerically equal to this current density, to this formula in terms of the current in the magnetic world, or the electric world as we used to call it, divided by this radius of the wire here in the fluid world. If you do that, what you end up with is a velocity flow, V, that matches exactly numerically the value of the magnetic field. In other words, it will come out to be mu naught I divided by 2 pi times distance away from the center. So it actually not only looks analogous to the type of flow pattern you would induce by rotating your wire, it turns out that it is exactly an exact numerical analog, every bit as exact as our electric world analog. Now in these cases, we're not actually going to do too much in terms of computing with this fluid flow model. I just want you to know that it actually works exactly the same way as it did in the electric field case, where we have an exact mechanical analogy. We will mostly be using this, though, to help us intuit what the magnetic field lines will have to look like, right? They will look, the streamlines of this fluid flow model will tell you exactly the direction that the magnetic field lines have to point. So the bottom line, then, of this model is that to build the fluid analogy, what you do is you take, you place all wires that were carrying current, right? All current carrying wires in the fluid, and as long as you do that, and set them rotating at this special angular frequency, omega equals mu naught I divided by 2 pi r squared. If you do all of that, then the velocity flow in the fluid will be exactly numerically equal to the magnetic field that those wires will generate when you allow the currents to go through them.